up to now, you understand that your bright fringe is where constructive interference occurs. Your dark fringe is where destructive interference occurs. Okay. Now, the bright fringe and dark fringe, or the constructive interference or destructive interference, whether it's going to be constructive or destructive, has something to do with the concept of path difference. Okay. Now, path difference is a very important part in this chapter. This one you really need to understand. Okay. So, as I mentioned to you, the formation of bright and dark fringes on the screen is due to the occurrence of constructive and destructive interference, respectively, at different points on the screen. All right. Whether constructive or destructive interference occurs is normally determined by the path difference of the waves at that point on the screen. Okay. Now, path difference is actually just defined as the difference in distance traveled between two waves to a point. Okay. So if I make an example of the two source interference of light using double slit, just now you understood that you would have bright, dark, bright, dark, bright, dark, okay, on the screen. But let's just single out one particular bright fringe right now, okay? Just now you had this one, the screen here. You have bright, 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 and bright. Let's just say that this is the center one. Okay, this is the center line. Okay, so you have bright and dark, bright and dark, bright and dark. Okay, now, the bright fringe is caused by constructive interference. The dark fringe is caused by destructive interference. But whether it's constructive or destructive in the first place is determined by path difference. So let's just say right now I'm interested in the first bright fringe that you see here after the center fringe. Okay, so that one is represented at this point here. Okay, now to be a bright fringe here, it must be constructive. So to get constructive here, you need to have a certain path difference, a difference in the distance traveled between the waves to a point. If you look at this portion here, this is your double slit. So I mentioned to you, your double slit has two slits. When the light moves towards the double slit, it will diffract, and then it will move outwards at two separate portions. Okay, you now have two source interference. Okay, so to make things simple, let's assume that the waves from S1 will arrive at this point, and the waves from S2 will also arrive at this same point. Now, if you look at the diagram, waves from S1 and S2, they do not travel the same distance. Okay, wave from S1 and S2 do not travel the same distance. You see, S2 travels like this. This distance is shorter. But wave S1, to travel to the same point, you see this one is longer. Okay, they don't travel the same distance to the same point. Okay, so the difference in the distance that they travel to that same point is your path difference. As far as the definition is this. Path difference is the difference in the distance traveled between two waves to a point. Okay, all right. So right now, what we'll tell you is this. The only way you can have a bright fringe is if you have constructive interference. And the only way you would have constructive interference is if your path difference is equal to a whole number of wavelengths. All right. So let's just go through this, the notes that was written here. Suppose this S1 and S2 emit wave crest at the same time. The sources are in phase. At point P on the screen, the wave crest from S1 will arrive later than the wave crest from S2, since wave S1 travels at a longer distance than S2. So I mentioned to you S2 travels a shorter distance. It will tend to arrive first at point P. But S1, because it needs to travel a longer distance, it will tend to arrive later at the same point. Okay, so the distance that the difference in distance, or the extra distance that has to be traveled by the other wave, is called the path difference. All right, so P will only be a point of constructed interference if the wave crest from S1 arrives a whole number of wavelengths later than the wave crest from S2. Okay, so what do we mean by this is, if you look at the next page, okay, just look at the next page, which is this one. For constructing interference, path difference must be equal to whole number of wavelengths. All right, just remember this one first. Just now I told you that wave S2 will arrive first at point P, okay, because it travels a shorter distance. So let's just say that wave S2 is this one right now. Is this red color wave right now. This is wave S2 after it has arrived at point P. Now wave S1, which is this one here, will arrive later than S2. Okay, S1 will arrive later than S2 because S1 has to travel a longer distance, so it will arrive later. So what if it arrives one wavelength later? Okay, one whole wavelength later. See, if you arrive one whole wavelength later, notice that this one is meeting in phase with this one. So you're going to get constructive interference. If you arrive, say, two wavelengths later, you will notice that this one is also still meeting in phase with this one. So you're going to get constructive interference. If you arrive three wavelengths later, your wave crest is meeting the wave crest of this. Your wave trough is also meeting the wave trough of this. They're still meeting in phase. Okay, so you see wavelength, one wavelength, two wavelength, three wavelength. If I repeat this for four wavelength, five wavelength, six wavelength, you will still expect to see the wave meeting in phase. Okay, this one is the condition for constructive interference. All right, the path difference equals to lambda. This one is for the first bright fringe. The two wavelength path difference is for the second bright fringe. The third three lambda path difference is for the third bright fringe. Okay, it is more for something like this. Let me show you. If I told you that this one is your bright fringe, this is the center one, the central fringe. This one here is your first bright fringe. Just now the concept was the path difference here must be equals to lambda. Only then this one will be constructive, therefore giving me the first bright fringe. What if I talk about the second bright fringe? So if I extend this, my second bright fringe is here, right? So waveform S1 and S2 will still need to travel from there to this point. So you have this line here like this, you have this line here like this. Okay, but you see, because it's more slanted now, the path difference is going to be larger. All right, That's why here the statement here I wrote there, the further away P is from the center line, the bigger the path difference. All right. So the further away you go, the bigger your path difference. So if I go further away from the center, this one is already my second bright fringe. My path difference is obviously going to be larger than before. Here, my path difference will be 2 lambda to give me my second bright fringe. If I go and extrapolate it for the third bright fringe, you can easily visualize my path difference is going to be even more. So my path difference here would be 3 lambda. Okay. So far, so good with this. All right. So to get your constructive interference, thereby giving you your bright fringe, you must have path difference of whole number of wavelengths. Okay. Now the same concept is used to explain your dark fringes also. Okay. Let's say right now, I thought about this one, the same point P, but this one is a dark fringe. This is where I have destructive interference. Okay. The same concept still applies. S2 will arrive at point P first. S1 will arrive later because it has to travel a larger distance. So the path difference will determine whether you're going to get destructive interference. So here what we'll tell you is that P will only be a point of destructive interference if the wave crest from S1 arrives an odd number of half wavelengths later than the wave crest at S2. Simply put, if your path difference is an odd number of half wavelengths, you're going to get destructive interference. All right. So let's have a look at it. Why? This one here, look back at the next page. Your wave S2 has arrived at point P first. Your wave S1 would arrive later. But how much later should it be to give you destructive interference? If it arrives half a wavelength later, you see the crest meets with the trough. So this is going to be destructive interference. This one would be more for the first dark fringe. So if I go further away from P, I will be going towards the second dark fringe already. The path difference is larger, but how much larger should it be? It should actually be 3 lambda over 2. When it's 3 lambda over 2, the crest here will meet the trough here. Again, you have destructive interference. So if I go further down again, further away from the center line again, now I thought about the third dark fringe. My path difference must be 5 lambda over 2. Only then will my crest meet with the trough. So here I would have destructive interference again. So from lambda over 2 to 3 lambda over 2 to 5 lambda over 2, you can see a pattern here. The next one should be 7 lambda over 2 or 9 lambda over 2, 11 lambda over 2 or 13 lambda over 2, right? Okay, so you see here, if you try to see this pattern here, you can actually generalize it as this: n plus half lambda. All right, all this is actually considered to be odd number of half wavelengths because you see lambda over 2. Wait, let me write it out properly. This one is lambda over 2, 3 lambda over 2, 5 lambda over 2, 7 lambda over 2, and then 9 lambda over 2. Okay, your odd number of half wavelength is referring to this. And this is 1, 3, 5, 7, 9. Okay, odd number of half wavelengths. It cannot be even number of half wavelengths. Okay, if you have even number of half wavelengths, 2 lambda over 2 or 4 lambda over 2, notice that this one will simplify to lambda, and then this one will simplify to 2 lambda. Lambda and 2 lambda is actually for constructive interference. Okay, so that's why the wording is a bit specific here. It must be odd number of half wavelengths. You cannot say it's multiple of half wavelengths. If you say it's multiple of half wavelengths, it could also mean this even number of half wavelengths, which in turn simplifies to this, which is talking about constructive interference. Okay, so the wording is a bit specific. Odd number of half wavelengths. Okay, so you generalize the equation, it will be n plus half lambda. All right, where n is 0, 1, 2, 3, 4. Okay, so far so good with this. All right. Okay, then another thing here that I will need to mention is this. Okay, all this while, your path difference here, when I mention the path difference here, these two sources are in phase. What do I mean by that is this. S1 and S2, this is what we mean by in phase. They are all vibrating in phase now. Crest coincides with crest, trough coincides with trough, and so on and so forth. This is when you're looking at this example, the sources are in phase. All right. In some questions later on, they will ask you, what if the two sources are 180 degrees out of phase? Okay. If the two sources are 180 degrees out of phase, it will mean something like this. Let's just say that S1 is like this. This one is in phase. Okay. If the sources are out of phase, S1 could be like this. S2 could be like this. Here you'll see that crest is meeting trough and so on and so forth. Okay, this is 180 degrees out of phase. 100 degrees out of phase. Okay, so in the event that the question somehow changed a little and they tell you right now the sources are no longer in phase, but instead 180 degrees out of phase, you will be expected to know what will be the changes. Okay, so just remember this now. When you see them changing the phase between the sources, the path difference required for constructive and destructive interference will be switched. The positions of constructive and destructive interference on the screen will also be switched. Okay, so what this one simply means is this. If I wanted to have constructive, my path difference would actually be n plus half lambda instead. If I wanted to have destructive, my path difference would be n lambda. Okay, it's the direct opposite of what you have before. Okay, this is if you change the phase difference of the sources. Okay, so this one is path difference. Okay, right, the path difference question is a question that does come up quite often nowadays, so it's good to understand it in detail. All right. Okay, so the last thing I will probably just mention to you is also for double slit. So just now I told you that when you want to see the interference pattern for light using double slit or Young's double slit experiment, you will have a pattern of bright and dark fringes. There is a certain equation that will always be related to the bright and dark fringes if it's double slit. That one will be this one. Okay. All right. For two source interference using double slit, the equation that will always apply is this: lambda is equals to AX over D. Okay, where A is distance between the slits, capital D is the distance between slits and screen, lambda is the wavelength, and then X is the separation between the adjacent bright fringe or adjacent dark fringe. So what you have here is your simplified diagram of your interference pattern after it goes through a double slit. So A is the distance between the slits, D is the distance between the slit and the screen. Okay, lambda is the wavelength, and then X is the distance between adjacent bright fringe or dark fringe. So you see here, I already indicated to you what is bright fringe and dark fringe. So if you're talking about adjacent bright fringe, this one and this one, the distance is X. Or if you want to talk about adjacent dark fringe, this one and this one is also X. Okay, so for now, just remember this equation. This equation you need to remember, all right? Eventually, you will have to use this a lot in your questions. All right. All right, so for last week, we were talking about two source interference. We talked about two source interference between water waves as well as light waves. The basic principle in which the interference pattern is formed is always the same. It always involves two sources, S1 and S2. All right, so source 1 and source 2. So the assumption is that these two sources are emitting waves, and the waves are moving outwards in a circular manner. So source 1 will have a wave that is emitting outward in a circular manner like this. And then source 2 also has a wave that is being emitted out in a circular manner like this. All right. So as these two waves propagate outwards in a circular manner, there will be certain regions in which they overlap. Okay. This part here is your interference region. Okay, so in this interference region itself, you will normally see what we call as interference patterns. Okay, the interference pattern is just simply regions in which you can clearly see constructive interference and destructive interference. That one is actually shown under page 6 of your notes. All right, so this one here was showing you two different wave sources. The waves are propagating outwards, and then there will be certain regions in which the waves interfere. So they interfere and they give you some sort of interference pattern. There will be certain clearly defined regions where constructive interference occurs and where destructive interference occurs. So in the interference region, you expect to see these regions here being constructive, and then in between these regions here being destructive. Okay, so for the ripple tank experiment and for the Young's double slit experiments, there were just different methods to look at the interference pattern. It differs because of the wave type that you use. If it's a water wave, when you want to see the interference pattern that is formed, you use a ripple tank. All you just needed to do is to shine a light onto the interference pattern, and the interference pattern will be projected onto a screen below. You're actually seeing the shadow of that interference pattern. Now, if you doing the same thing, but using a different wave type, let's just say for light, you will not be using a ripple tank, because if you try to shine a light onto an interference pattern of light, you don't expect to see a shadow pattern. Okay, so you have to use a different way of looking at the interference pattern. So that one is done using Young's double slit experiment, where what you do now is that you place a screen in the path of the lights as they're trying to propagate outwards, and then from there you'll be able to see a pattern of bright and dark fringes. So on and off, you'll be able to see a pattern of bright and dark fringes. Okay, right? So that one was the gist of what I mentioned last week. Okay, and I also mentioned the concept of path difference. So this one I'll just skip first. We'll recap it in the question later on. Okay, so the very last thing that I stopped at was equation for two source interference. Okay, in general, for any interference pattern that is formed due to two source interference, there is always one equation that applies, which is this one. Lambda is equals to AX over D, where A is the distance between the slits, D is the distance between slits and screen, lambda is the wavelength, and X is the separation between adjacent bright fringe or adjacent dark fringe. You can also think of it as separation between adjacent constructive interference or adjacent, or when you say it's adjacent dark fringe, is actually talking about adjacent destructive interference. Okay, so usually we tend to apply this for two source interference pattern formed by light, but it could also be applicable for some other wave types. All right, so here what you have is actually the interference pattern formed using light, using Young's double slit experiment. Okay, so the A here is the distance between the slits. The big D here is the distance between the slit and the screen. All right, lambda, as mentioned, is actually just your wavelength of the light that you've used. And then X is distance between adjacent bright fringe and adjacent dark fringe. So over in this diagram here, you see the red dot, that is bright fringe. You see the green diamond shape, that is the dark fringe. All right. So distance between adjacent bright fringes, which is this and this one will be X. Or distance between adjacent dark fringes, which is this and this one will also be X. Okay. So if you're talking about distance between adjacent bright and dark fringe, this one is actually X over 2. Okay, so if let's just say I'm talking about this one and this one would actually be X over 2. Okay, so for the interference pattern formed by light, one thing that you should know is this: the fringes are actually equally spaced. All right, the distance between any adjacent fringe will always be the same regardless of the distance from the center line. What we mean from here is that if I go further away from the center line in this direction, this one being the center line here, you will find that the distance between fringes will always be the same. This one will always be, as I mentioned, this is X over 2, 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 and this one is also X over 2. Okay, so it doesn't change. All right, it will always be the same, no matter how far away from the center line you go. Even if you go downwards here, it's also the same conclusion. All right, the distance between the fringes will always be same. It won't change. Later on, you will see it does change if we do something else. All right, so for now, just remember that if it's double slit interference pattern, the distance between adjacent fringes would always be same. Okay. All right, and then another thing here that I should mention to you here is the path difference. Okay, so whatever number is inside the bracket here that you see on the diagram is actually indicating to you your path difference. In the previous lesson last week, I mentioned to you bright fringe is actually due to constructive interference. And to get a bright fringe, your path difference must be equals to 0, lambda, 2 lambda, 3 lambda, and so on and so forth. You need it to be whole number of wavelengths. If you're talking about dark fringes, it is actually due to destructive interference. Here, your path difference will need to be lambda over 2, 3 lambda over 2, or 5 lambda over 2, and so on and so forth. So this one, if you try to generalize it into a equation, this is what you get, right? So to get destructive interference, you actually need an odd number of half wavelengths. So notice all of these are actually half wavelengths, but they are in multiples of odd numbers. Is either 1, 3, 5, 7, 9, 11, 13, and so on and so forth. Okay, yeah, for what I've just written here, in terms of the general equation that represents the path difference, just remember this, the ones that I've just written here, n is actually 0, 1, 2, 3, 4, 5, and so on and so forth. Okay, in your questions later on, especially in your paper 1, they will actually write something like this, where they tell you n is actually positive, values. N is actually positive integer values. Okay, so later on in your paper 1 MCQ, you also notice that they will talk about path difference, and then after that they tell you n is positive integer values. Just be mindful whenever you see this term, when they say n is positive integer values, this one just means 1, 2, 3, 4, 5, 6. Okay, it doesn't include 0. Okay, doesn't include 0. Okay, in cases like this where you see n is just positive integer values, you will need to change, there will be something that you need to be careful about. If they say n is positive integer value, what we'll just mention here is that destructive interference, the path difference is still going to be lambda over 2, 3 lambda over 2, 5 lambda over 2, and so on. But the general equation would be different now. It's actually n minus half lambda. Okay. Hi Regan, you just joined. We are under page 11. All right, we're still talking a bit about path difference from last week. Okay, so just be careful. Whenever you see in your questions and they talk about path difference, but the specificity n is positive integer values, just know that it's talking about 1, 2, 3, 4, 5, 6. It doesn't include 0. So when it comes to the destructive interference part, and they ask you what is the path difference, the general equation that represents the path difference for destructive interference is actually n minus half. Okay, because you see, if I start with 1, 1 minus half will give me lambda over 2 lor. 2 minus half will give me 3 lambda over 2 lor, and so on and so forth. Okay, all right, so just be careful about this. If I assume it was 0, 0 minus half will give me negative half. This one is not valid. Okay, so just be careful. All right, if it's in this form, n minus half lambda, n must be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, okay. But if it's n plus half lambda, n is 0, 1, 2, 3, 4, 5, 6. Okay, so just be mindful of this slight difference. All right, so back to what I was talking about. When you are talking about the bright and dark fringes on your double slit, okay, when you're talking about the bright and dark fringes on your double slit, you won't have alternating bright and dark fringes. You're also supposed to know what is the path difference for each of the corresponding bright and dark fringes. Okay. If I talk about the center line here, the path difference is actually 0. Okay. Why do I say the path difference is 0? Because if you imagine this one is source 1 and this one is source 2, wave from source 1 will travel this distance to the center line. Wave from S2 will travel this distance to the center line. You see, they travel the same distance to that same point. So your path difference is 0. Last week I mentioned to you, path difference is the difference in distance traveled between 2 points to a wave. Specifically for the center line itself, your path difference is actually 0, okay? Because they travel the same distance. But if you're talking about path difference to the first bright fringe after your center line, say maybe this one here, okay? This one, wave S2 will travel this length, wave S1 will travel this length. There is a difference in the distance traveled. This one is your path difference, okay? So for constructive, it must be whole number of wavelengths. If this one is path difference 0 at the center lines, this first bright fringe after the center lines must have a path difference of lambda. The second bright fringe must have 2 lambda. The third bright fringe must have 3 lambda, and so on and so forth, okay? You can also do something similar for dark fringes, okay? For dark fringes, you again have waves that are traveling different distances to that particular point. So let's just say I talk about this one. This is the first dark fringe after your center line. Wave S2 travel this length, wave S1 travel this length. Again, you have path difference in distance travel to that same point. Okay, so in your case, your path difference is actually half lambda. But as you progress further away from your center line, the subsequent dark fringes would have 3 lambda over 2, 5 lambda over 2, and so on and so forth. Okay, so learn to identify this pattern when it comes to looking at the constructive and destructive patterns form. Okay, so this one is just one thing I needed to mention. Okay, then after that, as I mentioned to you, any interference pattern formed by two source interference pattern, this equation will always apply. Lambda is equals to ax over d. So a lot of times they will ask you, if I want, say for example, the fringe separation between the bright fringes to be larger, what is it that I can do to the apparatus to make sure the separation is larger? So you look at this equation, lambda is equals to ax over d. You make x the subject, it becomes lambda d over a. If you want x to be larger, lambda must be larger, d must be larger, or a must be smaller. Okay, that's what this one here is talking about. All right. And then this one here on the second statement here, where we tell you when x increases, the separation between fringes increases, the area of the bright fringes is actually larger. The intensity is spread out over a larger, so brightness decreases. All right. What we mean by that is something like this. If you look at your pattern of interference fringes on the screen, let's just say that this is your center line. Your fringes could look like this right now. Okay, where this one we tell you is x, all right, distance between adjacent fringe. Now, if your separation is somewhat larger, Maybe I draw it at the top. This one still being your center. Your separation between fringes is now larger, but at the same time, when the separation becomes larger, your fringe actually will appear bigger. It will look something like this. Okay, so maybe I better just draw it here. If this one was your X, now your X is like this. It's still considered to be larger separation between bright fringes. But what you'll notice is that the area has actually now become bigger. The area has actually become bigger. Your light is actually spread out over a larger area, so your brightness is actually going to decrease. Okay, so this is one thing if they ask you about what happens to the brightness of the bright fringe. The brightness of the dark fringe itself will remain unchanged. Okay, so this one, no worries. Okay, then after that, there are also some other changes that you can do. Those are listed over here. All right. So if one of these following changes were made to the wave source separately, all right. Now, one assumption here is that when you want to produce the interference pattern using two different sources, in your case, a double slit here, you normally assume the wave sources are in phase. Okay, what I mentioned to you as being in phase is something that looks like this. If this is S1 and this is S2, they vibrate in phase like this. Crest with crest, trough with trough, and so on and so forth. Okay, so usually you will notice this whenever you talk about two source interference pattern. The assumption is that your wave sources are always vibrating in phase. Okay, so this one, just bear this in mind first. All right, right now what they're telling you is that the intensity of both wave sources are increased. What do you expect to see for the pattern of bright and dark fringes? Okay, so if you're talking about the intensity of both wave sources being larger now, wait on, let me just erase this. Just now I wrote here something like this. Okay, if the sources were in phase, what I meant was that the waves look like this. Okay, crest will be with crest, trough will be with trough. This is what in phase means. Okay, in other words, the phase difference between them is 0. Okay, now if the first change that you make here is that we tell you that the intensity of both waves is increased, you learned in the previous chapter waves that intensity is proportional to amplitude squared. If you were to increase the intensity, your amplitude would actually also increase by right because of this relation. So right now, if the intensity of both wave sources at S1 and S2 are increased, what you expect to see is that the wave amplitudes ought to be larger. Okay, the wave amplitudes is actually larger now. But what effect would this have on the pattern of bright and dark fringes that you have here? Okay, so what we'll tell you is that the bright fringes will actually become brighter because amplitude of new resultant wave is larger during constructive interference. Now, this part here is for here. Okay, Now this part here, you would have separate diagrams to represent it. If let's say you're talking about constructive interference, let me erase this one. If you're talking about the pattern where you have constructive interference, the general idea is that the waves must meet in phase. It's a bit the same like your initial diagram. Okay, crest meets with crest, trough meets with trough. Okay, this one would be for the bright fringes here. All right, crest is meet with crest, trough is meet with trough, so that you get larger. Okay, now maybe I cannot draw it here. Draw on the left side. Okay, so that your new wave would be larger. Okay, this one is for the constructive interference. Wave from S1 is like this, wave from S2 is like this, they are meeting in phase, giving you an even larger resultant wave. That's how you got your bright fringe here. So right now, if you say your intensity of both wave sources are now increased, your amplitude from your source is actually larger. Okay, so that will mean that when your waves from S1 and S2, once they arrive here, they will also be having a larger amplitude like this. Okay, they will still be emitting in phase. All right, but now because your amplitude for each of the wave sources is now bigger, your resultant amplitude would be even bigger still, like this. Okay, that's why here we say that the bright fringes will actually become brighter. Your amplitude, because your amplitude of your new resultant wave is actually larger than before. Okay, but if you look at what happens to the dark fringe, what we'll say is that the dark fringe remains dark because complete cancellation of waves still occur during destructive interference. Okay, so what's happening here is something that looks like this. At the dark fringe side, at the side where you have your dark fringe, wait on, let me just erase some of the stuff. At the side where you have your dark fringe, that is where you have your destructive interference. Okay, so your waves could be meeting out of phase. Okay, if this wave meets with this wave like this, maybe I better draw it like this. This one is considered to be constructive. Okay, but if this wave meet with the bottom wave like this, if it was destructive, it should be like this. Okay, where we say crest meets with trough, and then trough meets with crest. In cases like this, if you say this wave plus with this wave, this one is actually destructive interference. Okay, your resultant wave would actually look just like this. Okay, it will just be nothing, right? This one is if before you have any changes. But if let's just say your intensity of both wave sources are increased, your amplitude is now larger. So this one would have a larger amplitude now like this. Okay, so now this meets with this one, meets with this one. They're still meeting our phase, and assuming that the amplitude is still the same, you're still gonna get back that same flat line here. All right, this one you see it did not change because complete cancellation of the waves are still occurring. All right, so your dark fringe actually has no effect. It still remains dark. There's no changes in the brightness. It did not become darker. It did not become brighter. It still remains dark. All right, because here your waves still completely cancel each other off. All right, so this one should be okay. Right, this one is what happens when you have intensity of both wave sources being increased. Now another one would be what happens if only the intensity of a wave source is reduced. Okay, if you look at the second page, what happens if the intensity of only one wave source is reduced? The previous one was you increase the intensity of both waves, so meaning to say you increase the amplitude of both waves also. But now this one here, we tell you you reduce the intensity of one wave source only. Okay, so what would then happen for the pattern of constructive and destructive interference that you see? So if you are only reducing the intensity of one wave source, that would mean only the amplitude of one of the waves is less. Let's just say that maybe I reduce the intensity of wave S1 for this. That one, the reduced amplitude is represented by this orange colored line. Okay, it is now lesser than before. Okay, this one is amplitude being reduced. Okay, so now what do you think would happen to the pattern of constructive and destructive interference that you see? So if S1 now has a smaller amplitude represented by this orange line here like this, at where you have your bright fringe, constructive interference still occurs. They're still meeting in phase, crest meets crest, trough meets trough. You're still gonna get a larger wave, but it's not that big as before. Sorry, but it won't be as big. You look something like this. A smaller amplitude add with the original will give you something like this. Okay, right? You're getting something like this, represented by the orange line. Okay, a smaller amplitude now meets out with the original amplitude. You're gonna get something like this. Okay, it's gonna be smaller compared to the original one. All right, so that's why here we'll tell you the bright fringe is actually less bright because the amplitude of the new resultant wave is smaller now during constructive interference. Okay, so if let's just say that this one was, maybe I should give you some values. If this one was A, and then this one was A, this one add up will give you 2A. If this one was, say, 1.5A, and this one is also 1.5A, you add up, it becomes 3A. If this one was, say, 0.5A, you add out with A, you're gonna get 1.5A. Okay? So your new wave during constructive interference is actually lesser than the original one. That's why it's less bright. Okay? Now, what do you then think would happen to the dark fringe? Okay, so let's just say right now the dark fringe, I'm talking about the dark fringe. I get rid of some of the highlighted sections here. For the dark fringe, I know you're talking about constructive interference. So the waves meet out of phase right now. If you saying right now one of the waves has a smaller amplitude at 0.5, okay, it meets with the wave of with the original amplitude of A. Let's just say that this one is A right now. Okay, this one is negative A. This one is negative 1.5A. If I say this 0.5A meets with negative A, 0.5 minus A will give me negative 0.5A. You see here, complete cancellation doesn't occur. If one of the wave sources with reduced amplitude, if one of the waves with reduced amplitude meets up with another wave of the original amplitude, they do not completely cancel each other off. Okay, they won't completely cancel each other off. So you're gonna get some sort of residual wave that looks like this. If this meets with this, you're gonna get something that looks like this, where the amplitude is negative 0.5A, and then the amplitude is A. Okay, so here you will see that your waves don't completely cancel off. Complete cancellation of waves does not occur. All right, so your dark fringe is actually going to be less bright. Okay, it is not a flat line as before. Okay, if it's a flat line, it will be completely dark. But if it's not flat, you have a little wavy wave profile here like this. This one is telling you your fringe is actually not as dark as before. Okay, so complete cancellation of wave does not occur. This one I said refer page 5. It's something that I explained in the first lesson last time over here. If you want to have complete cancellation of waves during distracting interference, your amplitude must be equal in the first place. But if your amplitude is not equal, like the ones that I see in this diagram here, you will get some sort of wave remaining, but it's not as big as before. It's actually much smaller. Okay. Right, so that one is what I mentioned. Wait, now let me just go back to the original page. Okay, right, so this one is if intensity of one wave source is reduced. Okay, the diagram that I have here looks a bit messy because I'm trying to combine them together. I don't have much space to draw here to explain. That's why it looks kind of messy with all the different waves combined together. If you want to, you can actually draw out those little diagrams that I've drawn here separately, individually, in any space you have in your notes. In my case, I don't have space in the screen. That's why I have to combine them together. That's why the explanation looks kind of messy. All right, but if you want to have a better understanding of what I just mentioned, I would suggest that you try to draw out the individual waves separately. Maybe for one, you draw out one set. For two, you also draw out one set. It will help you to see better. Or if you don't want to, you can just draw it all combined like I just did. If you printed out the notes already, I would suggest you draw it all the way at the back part of your notes where there's a blank page. Okay. Right. Okay, now let's move to that last part. Okay, wait now. I just need to go through a bit more before I can just do your past years. Okay, the last one here is where we tell you what happens if the wave sources are 180 degrees out of phase. Just now, the first thing I mentioned to you just now was that you assume that the wave sources were in phase, meaning to say it look like this. Crest meets crest, trough meets trough. Okay. if the waves were now out of phase, when we say out of phase, generally we mean phase difference being 180 degrees. This one in phase, we normally mean phase difference between the waves is actually 0 degrees. Okay, so when we say the waves at the source are now out of phase, it implies maybe this wave is like this, but the other wave is like this. Crest meets with a trough, crest meets with a trough, and then a trough meets with a crest. This is out of phase. Okay, so let's just say right now, if wave S1 and S2 are no longer in phase, like what you see here, instead they are out of phase like this, what do you suppose will happen to the interference pattern that you see? Okay, so what we'll tell you is that everything will switch position. Point where constructive interference occur becomes destructive and vice versa. Right? So constructive will now become destructive, destructive will now become constructive. So where you normally see bright fringe, it now becomes dark. When you normally see dark fringe, it now becomes bright. What I mean by that is that if you look at this little diagram again, what will happen is that I should use a different color, maybe I use this one. Okay, what will happen is that if you look at this interference pattern here, everything will now switch position. The center line here, it was originally bright, right? It is now dark. So every bright fringe that you have here, 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 has now all become dark. And then where you have destructive interference, giving you dark fringe here, 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 and here, they are now no longer dark. They are now all constructive. Okay, that's what we meant just now by this statement. If you suddenly switch the wave sources so that they are 180 degrees out of phase, constructive will now become destructive. Therefore, bright fringe will now become dark fringe. Okay, and vice versa. All right, and now another thing you also should know is that if you want to have constructive interference right now, your path difference is n plus half lambda. If you want to have destructive interference right now, your path difference is n lambda. Okay, because you see here, if you look at this diagram, dark fringe, this one, this one, this one, is now having path differences of 0, lambda, and 2 lambda. All right, and then you look at where you have your bright fringe, where you have constructive interference, your path difference is now half lambda, 3 lambda over 2, 5 lambda over 2. Okay, so the path difference would also switch. If before this, constructive interference was whole number of wavelengths and destructive interference was odd number of half wavelengths, the position has now switched. Okay, constructive will now be n plus half lambda, destructive will now be n lambda. Okay, so this is one thing you need to know if they ask you. This kind of things that ask you to describe what happens to the interference pattern when you do any of these changes. This is usually in your state and explain questions. All right. So what you have here is actually all the possible kinds of state and explain situations that you have. So it may seem a bit confusing right now, but over time, when you do more and more of it, you start to see a pattern here. Okay, so needless to say here, I'll just mention to you, n is 0, 1, 2, 3, 4. It includes 0. Okay, all right. So there are just 2 other situations where I need to mention to you before I do your past years. All right. Okay, now you can also have 2 source interference pattern with other wave types. The ones that we've just mentioned is only for water waves as well as for light. you can have two source interference pattern produced by other wave types also, such as for microwaves as well as for sound. Okay, so the basic principle in which the interference pattern is formed is still the same. All right, the only thing that's different now is how you detect the interference pattern. Okay, so what we'll say here is that if you want to find out, when you want to study the interference pattern formed by microwaves, what you do is that you have a microwave transmitter here that acts as your source of wave. You have a pair of metal slits here. You have metal sheets here that have gaps between them. You see there's a gap here and there's a gap here. These are actually equivalent to your slits, so that when your microwaves passes through these metal sheets with the two slits, you get two separate sources of wave. You get one wave coming out here and one wave coming out here. All right, so now you have two sources of wave. If you look at it from the top, it looks like this. Okay, your source of wave is here. It hits the metal plates with the two slits. So once it hits the metal plate with the two slits, each slit acts as a wave source itself. They diffract. Okay, the wave passes through each slit, it diffracts, it becomes a wave source. So slit P and Q will be two different wave sources. So P would have wave coming out, Q will also have wave coming out. So there is a region where again they overlap. You would have certain clearly defined regions where you have constructive and destructive. So you expect to see something like this. This part here represents all your constructive. Right, the brown colored line here represents your constructive. And then in between, you will have your destructive. Okay, so what you want to do then is that if you want to detect the interference pattern, what you do is that you move a microwave detector. Okay, you move a microwave detector along a line like this. Okay, so as you move your microwave detector along a line that looks like this, you will hit certain regions where it is constructive, certain regions where it's destructive. If I try to mark out all your constructive regions, this one is C, 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 C. This one is D, 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 right? Okay, so what will happen is that when you move your microwave detector, you start to read maximum and minimum readings of intensity from your detector. Okay, so maximum and minimum readings on your detector actually correspond to your bright and dark. Sorry, in your case, it's not bright and dark range because you're not talking about light. Your maximum and minimum readings actually correspond to regions of constructive and destructive interference. Maxima corresponds to constructive. Minima corresponds to destructive. Okay, so by moving your microwave detector along this line here, you will hit regions of constructive, regions of destructive. How you know you've hit regions of constructive interference? You just see whether you have a high meter reading. How you know you have hit a region of destructive interference? You will see a low meter reading. Okay. Sometimes the region of constructive or destructive interference is also known as maxima or minima. They tend to use the term interchangeably. Okay. Right. So this one is if you're doing it for microwaves. Now, the same can also be said if you're trying to do this, if you're trying to do this with sound waves. Okay. You're trying to do this with sound waves, it's the same thing. What you do is that you will connect two loudspeakers to a signal generator. Okay, these are your two loudspeakers. You connect it to a signal generator. The reason why you want to connect two loudspeakers to a signal generator ensures that the sound waves generated are of the same frequency and hence are in phase. In other words, they are coherent. Okay? In other words, they are coherent. All right. So same thing with before. Your loudspeakers will now produce their own waves. There will be certain regions where they overlap. You're going to have an interference pattern form. So the interference pattern that is formed will look something like this, where certain regions are constructive and destructive. Something like this. Okay, so this is where all your constructive occurs. The destructive is the region in between. Okay, so how you want to detect those regions of constructive and destructive interference? You use some other method of detecting it. You don't, you cannot see sound, all right? You cannot shine a light on it and expect to see a shadow of sound, all right? So one of the ways in which you can detect the constructive and destructive region is that what will tell you is that you carry a microphone and then you move it along this direction from P to Q, all right? What you will be noticed is that the loudness of sound detected will rise and fall, okay? Where you're getting a loud sound, that is where constructive interference is occurring. When you're getting a soft sound or no sound, this is where destructive interference occurs. All right. So this is due to interference of sound waves, where regions of constructive interference cause loudness of sound to increase, where regions of destructive interference cause loudness of sound to decrease. Okay. So all this is two-source interference pattern. The method in which they are produced is always the same. It's just that the way you would detect them would vary depending on the wave type. If it's water wave, it's a different experiment. If it's a light wave, it's a different experiment. If it's sound wave, microwave, you also use a different experiment. Okay, that is the gist of it. Okay, so that should be that. Okay, now that we've gone through the two-source interference pattern, I can go back to something that was from a very early part in your notes. If you look at page 5 of your notes, all right, I believe I explained this part only for you guys. All right. Right. So I'll explain this entire thing in full for you now that you've gone through two-source interference of light. Okay. So let me just clear off everything. I'm trying to draw something here. When it came to the two-source interference of light, the diagram that I drew for you look like this. You have a beam of light that comes here, and then you have this. Okay, so you have these dots here representing a bright fringe, and then you have these crosses here representing your dark fringe. Okay, so bright, 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 and bright, and then dark, 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 and dark. Okay, now a lot of times when you're talking about interference pattern, this thing here, the pattern of bright and dark fringes, is known as your interference pattern. Okay, if you can see this one, this one will also be considered as your interference pattern. All right, whatever you can see a pattern, that is called your interference pattern. All right, but for let's just say the case of interference using light right now, when we talk about the interference pattern, we are actually referring more towards the bright and dark fringes that is formed on the screen. So some other further questions may ask you, what are the conditions for steady interference pattern? Okay, now the word steady here means the pattern does not change with time, okay, i.e. location of bright and dark, location of bright and dark. Okay, maybe I just rub this one. Location of constructive and destructive interference does not change. Okay, right. When we say steady interference pattern, it normally means that the pattern does not change with time. Okay. All right. So meaning to say the location of constructive and destructive interference does not change. If you're looking at the diagram that I just drew here, if this one is a steady interference pattern, let's just say at time t equals to 0, I see the bright fringes here and the dark fringes in between. If I let time pass, maybe t equals to 1, t equals to 2, t equals to 3, all the way to t equals to maybe 300 seconds, it will still be the same. Bright is where it is at since the beginning, dark is still where it is at the beginning. If the pattern is not steady, these locations of your bright and dark fringe will start to change. It could be that maybe t equals to 0, you see your bright fringes here, but then at t equals to 1, your bright fringe suddenly changed to this location, and then your dark fringe suddenly changed to this location. Okay, and then when you go to t equals to 2, again they change position to some random position. Bright can go to here, dark can go to here, or some other random positions. That is what non-steady interference pattern is. The location where you get your constructive destructive, or the location where you get your bright and dark will change. Okay, so apply in the context of light, constructive is bright fringe, destructive is dark fringe. So you normally want to have an interference pattern that is steady. It does not change with time. It does not change location with time. So in order to get a steady interference pattern, one of the most important things is that the waves that form the interference pattern must be coherent, having constant phase difference. Remember before this, I mentioned to you coherence is actually just indicating constant phase difference, which in turn implies the waves must have same frequency, period, speed, and wavelengths. All right. So that time I explained to you, if the waves are coherent, no matter which pair of points you pick, you will always have same phase difference. But on the other hand, if you do not have coherence like this one here, I think that the example was here. All right. If your waves are not coherent, that time I showed to you, your phase difference actually varies. Sometimes it's 0, sometimes it's 180, sometimes it's 90, sometimes it's 270. So it's because you do not have constant phase difference, your location where your constructive and destructive interference occurs will not be constant also. All right. That's the reason why we tell you, if you want to have steady interference pattern, so that your location of constructive and destructive does not change, your pattern does not change with time, you must have coherence so that you have constant phase difference. All right. Okay. And also you will notice that in all those little experiments that we've described just now, that gives you interference pattern, you normally have the wave sources derived from a single point first, or single source, to guarantee constant phase relationship, to guarantee that they are coherent. Okay, so that is steady interference pattern. All right. And then another thing here would be for your interference pattern to have good contrast between maxima and minima, the amplitudes must be equal. Good contrast here, you can just think of it as clear difference. Okay, you can see a clear difference between maxima and minima. Okay, So if you're talking about interference pattern and you're talking about, say, interference pattern formed by light, you have bright and dark fringes. If you want to have good contrast or clear difference between the bright and dark fringes, what you should do is you ensure that the amplitudes are equal. All right. So if your amplitudes are not equal, I mentioned just now to you, during the destructive interference part, complete cancellation of waves will not occur. All right. So if your complete cancellation of waves do not occur, you will get some sort of residual wave. Okay. So what will happen is that your dark fringe is not completely dark. Okay, so your dark fringe is not completely dark. It has some faint light to it. If you compare with a bright fringe, dark fringe and bright fringe now both have light. It's just that dark is slightly fainter. Okay, so if you're talking about contrast, then the contrast between the patterns is not good, because here bright fringe already has light there. The dark fringe also has some light here, so you can't clearly see the difference between them. In order to have very good contrast, you need to have both amplitudes equal. So as I mentioned to you, if both amplitudes are equal, you would have complete cancellation of your waves during destructive interference. So your dark fringe is completely dark, and then your bright fringe is the only bright spots there. So you can clearly see the contrast between bright and dark fringes. Okay, so just bear this in mind. Be careful of what the question is asking you. If they're asking you about the contrast or the difference between minimum, maximum, or bright and dark fringes, just know that you're talking about amplitudes must be equal. But if they're talking to you about steady interference pattern, they're talking more about the pattern not changing with time. So in order for your pattern not to change with time, you must have constant phase difference or coherence.